Hey everybody, I want to clarify this symbol here. This is the index of the radical is actually, let me just see if I can make this big enough. In other words, the square root of x, or excuse me, that this object, I couldn't even make it big enough here. I meant to make it large enough, but this is the index of the radical and it belongs in here, this whole circled object. For me, I'm afraid of writing large, I guess. But, and then you have x right here. So that's what I've intended here. I couldn't get the Microsoft editor to put this inside there. I guess it would make the symbol too distorted. But we're looking for all positive x such that this is true. Now it does depend on this expression called the ceiling. And so let's just briefly, I've done quite a few of these and this is the definition I use. Like say if you wanted to do the ceiling of, I don't know, 31, 32 over 5 maybe. Okay. It's the largest integer, or it's the smallest integer that's greater than the input argument. So this would be equal to 7. Okay. And that's simply because 6 is less than 32 over 5 is less than 7. Okay. All right, now let's get into the business of solving this equation. Y'all, the piecewise function, notice it determines an interval in a piece. The ceiling function determines sort of a piecewise interval of length 1, and so that's what I'm doing here. And this is just brute force, folks. I'm starting at 0 and working my way up. Any x that's between 0 and 1 has a ceiling of 1. That's a fact. That's definitely this definition, just a special case of this definition, right? So if you're an x residing in this interval, you have a ceiling of 1, okay? So what we do here is, you can see exactly what I did. I took the original equation and I simply put a 1 right here, right? See, we're assuming that the ceiling of x is 1, which determines this range of x's. And so I just wrote it down right here. In other words, this statement right here is exactly this statement. All right, and so if you raise both sides to the 5th power, you get x is equal to this number, and this number is greater than 1. So you see that means x is not in this interval. So you see, in other words, the interpretation there is this is not a solution. Okay, not a solution. SOLN abbreviated. Okay, and again, folks, it's because the number we got when we played by the rules is a number larger than the interval that's specified by any x that has a ceiling of 1. Okay, so not a solution. And again, I won't spend too much. This one's even clearer. It's the very same process, folks. Notice how 6 appears right here because, again, we're assuming the ceiling is 2. We're just marching our way and spanning all the real numbers, at least for a while. So anyways, the 6 comes from the fact you added 2. You put a 2 right here, right? Okay. So again, if you carry on in a similar fashion, you'll get x is not in this interval, right? So this is not a solution. Okay, not a solution. You see, the drawback to my brute force method here is that if the constants were too big, this would be painful, you know. Now right here, you can, again, you see how we go from 6 to 7. We assumed a ceiling of 3. And so this 7 here, since that thing's out of view, is 4 plus 3, right? Remember, it was the ceiling of the number plus 4. Okay, we're assuming the ceiling is 3. And again, that's, it's hard to keep everything on the screen, but that's just plugging directly into this, the problem we're trying to solve. All right, and so it turns out this number is, okay? And again, it's not trivial. I'm not going to prove it for you, but 2 is between, 2 bounds this number from below. And actually, it's a little bit of an exercise to show that without a calculator. Okay, so I'm not gonna slow down the video by doing that. But it turns out this is true. Okay, and it's pretty believable if you just look at it. But the square root of 3 makes it kind of ugly in terms of, without just using a calculator, you wouldn't know this, but there is a way to prove it analytically. Okay, so this is a solution. So x equals is a solution. Okay, now again, so we've done the floor level of 3. Now let's do the floor level of 4. Again, I just recopied our equation, folks. If we do a floor level of 4, you get an 8 right here, of course. And now this one's pretty easy to see. It's pretty easy to see that the ceiling of our candidate here, since there's no irrational numbers in there, the ceiling of 256 over 81 is equal to 4, right, folks? You can see that this is between a multiple. It's between 3 times 81 and 4 times 81, right? So that, by the definition. So this is another solution, okay? So we have two so far. We have this circled solution up here, and we have this solution. And this is how I designed the problem. I thought this was the only solution. When I started trying to work the problem, I found out there was another solution. It's kind of interesting. I designed the problem to have this as a solution, which is pretty trivial to do that. But I was slightly surprised when we had another solution here. All right. Now, again, if you can carry on here, you can see that none of these are solutions. Okay, and I won't do the work, but it turns out this number is less than 4, actually. Okay. So no solution here. And again, I went on just a little bit longer. There's also no solution here. And again, the numbers are pretty easy to check here. You can see clearly that this number is not in between 5 and 6, right? Because this is a number between 4 and 5. It's pretty easy to tell that, right? I think. Yeah, because 4 times 243 is what is that? 972, right? 972. All right, so, but anyway, not a solution. Okay, now, but I think I have a proof that these are the only two, folks, and it may not be very convincing to you. It's just taking larger and larger roots, get smaller and smaller numbers, but there's a well-known result from analytical or from real analysis. If you do limit as n approaches 1, n approaches infinity, my God, n approaches infinity of the nth root, and I'm going to put they don't usually put the constant here, but it's useful to put the constant just to make it more convincing. Of course, you can just bring the constant out and it'd be the nth root of k, right? But this limit is actually equal to 1, all right? So that's basically the structure that's going on here. You're upping the index, right? You're upping the index of the radical, and that's really jacking the number down quite a bit, right? So I think this limit pretty much is, I wouldn't call it rigorous, but a fairly convincing statement that there's not going to be any end of solutions. It's just that when you're close in for small n, this thing may move around or get a little bit larger, but the bigger this index gets, the smaller the number it gets. All right, and so anyway, that is it, folks. I'd like to know if you thought that's convincing enough. I think we could probably make it more algebraic and prove it more conclusively, but I'm gonna take this as a proof that if I didn't make any mistakes on these others, that there's only two solutions. This guy right here. Okay, thanks for viewing.